Let's jump straight into an explainer that is literally going to flip everything you thought you knew about computational energy waste completely on its head. We're looking at a radical new framework here, one that ditches those abstract mathematical infinities we've relied on for decades, and instead grounds our microchips in pure finite physical geometry.
Here's the roadmap for this breakdown. We're going to cover the infinite computation trap, enter side A normalization, explore the silver diamond balance, look at the global remainder register, see how halting at step 6 works, and finally, look at a massive 74x energy breakthrough. Let's get into it.
Section 1, the infinite computation trap.
We have to kick things off by calling out this invisible, massive drain on our world's resources, the infinite loop built into traditional computing logic. Which really begs the question, right? What if pure geometry could actually stop computers from wasting massive amounts of energy? This is a huge deal because it challenges the absolute bedrock of quantum electrodynamics, or QED. Currently, QED models elementary particles as zero-dimensional points. But, well, when you divide by zero, what happens? You generate mathematical infinities. Historically, giants like Feynman had to rely on a math trick called renormalization, literally subtracting infinity from infinity just to make the models work. Feynman himself actually called it hocus pocus. But what if we just didn't need the hocus pocus in the first place?
And that brings us to the elephant in the room for modern computing hardware, unhalted drift. Think about standard execution like Zeno's classical paradox. You know, Achilles endlessly chasing the tortoise across a decaying fraction of space, but he never actually reaches a definitive boundary to just stop. Because our current silicon architecture allows for this continuous floating point drift, it's constantly running in these unquantized spaces. And what does that do? It constantly generates heat and demands an endless supply of metabolic energy from the system. It's a massive data drain. So the contrast between our current setup and a truly sovereign system is pretty staggering. On one side, you have our standard top-heavy architecture with this infinite linear drift that literally just burns energy until the chip overheats. On the flip side, we have what the source material brilliantly calls the tortoise balance. This uses perfect quantization to enforce a physical deterministic halt. It essentially creates an armored system that knows exactly when to just stop.
Section 2, enter side A normalization.
Okay, so how do we actually fix this infinite drift? Well, we swap out those zero-dimensional points for finite, physical, geometric constraints. This is a concept called side A normalization, and it anchors a horizontal base perfectly to the unit axis. So by setting this horizontal base, our A equals 1 exactly to 1 on a continuous physical triangle, we completely eliminate those messy, never-ending coordinates. Instead, we are dealing with strictly rational algebraic inputs. The wave trajectory gets pinned directly to the crown of a unit circle. And because this physical tile area scales down deterministically to an absolute bit-perfect cutoff, Achilles isn't endlessly chasing the tortoise anymore, he's riding it. In geometric terms, the physical tile area is defined as the exact cross-sectional area needed to seal a central torus hole. Basically, imagine perfectly plugging the hole of a donut. Once that gap is perfectly sealed, the xenodrift just stops entirely. The system locks down into a sovereign state.
Section 3, the silver diamond balance.
Now let's see how this geometry gets hardwired directly into the physical circuitry level using a very specific equilibrium. To map this beautifully onto a two-dimensional hardware plane, the researcher introduces the silver diamond balance. Think of this as an isosceles one-to-one equilibrium. The horizontal infrastructure base, our A parameter, is locked at 1, and the vertical governance rise, our B parameter, is also exactly 1. Together they form this highly armored fourfold symmetric rhombic lattice. So here is the really crucial part. This specific decay parameter value, 0.4142, which is mathematically derived from the square root of 2 minus 1, sets the absolute geometric rule for our new, highly efficient hardware state machine. It's the exact mathematical ratio governing how the system scales down, perfectly, without ever drifting into infinity.
Section 4, the global remainder register.
To actually enforce this geometric rule inside a microchip, you need a physical mechanism to track the computation. Think of this global remainder register as a strict energy arbiter baked right into the hardware itself. It's constantly tracking something called accumulated metabolic potential, which is designated as DN. It's basically evaluating exactly how much spatial area, or potential, is left before the system is forced to cut off the computation entirely. Here is how it operates as a physical safeguard. The register tracks that potential and checks it against what the author calls the heticity floor. Now, this floor is basically an uncrossable hard deck, a fixed-point arithmetic boundary mapped for a 64-bit architecture. When the accumulated potential hits this absolute floor, the hardware controller doesn't politely ask the software to stop. It executes a physical metabolic pruning strike. It literally strikes the process down, completely bypassing those continuous, heat-generating SRAM loads that totally plague modern silicon.
Section 5, halting at step 6.
And now we hit the climax of the circuitry design, executing the physical deterministic halt. This step-by-step inward spiral shows us exactly how the hardware packs data. Working under that silver-diamond balance we just covered, right at step 5, the individual tile area contracts down to about 0.029, perfectly packing addressable data buckets. The inverse scaling hits a multiplier of roughly 198, sitting totally safe below standard hardware limits. But watch what happens at step 6. At n equals 6, that inverse scaling jumps to roughly 478, violently exceeding the 256 resolution ceiling of an 8-bit integer. Now, you might be thinking that sounds like a crash, but crossing that 256 ceiling isn't a bug. It is a meticulously designed feature. By mathematically forcing the hardware to blow past the 8-bit integer ceiling right at step 6, the system contracts its addressable resolution into a single macro block, and this instantly triggers a physical deterministic halt via an O-shift quadrant bit shift. In plain English, the hardware physically shifts the data bits to forcibly cut the power. The computation is physically forced to stop. No infinities, no drift.
Section 6, a 74 by energy breakthrough.
So let's talk real-world payoff. What happens when you implement this silver diamond balanced geometry into a physical CMOS 28nm chip? Well, by replacing traditional logic pipelines with SIDA reciprocal shifts, the energy savings are staggering. Just looking at the benchmarks, standard floating point 16 multiplication eats up 3.70 picojoules of energy. Standard addition takes 0.10. But the SIDA reciprocal shift, running on this bit-perfect geometry, it takes just 0.05 picojoules. That is an astonishing 74 times reduction in computational energy. By engineering hardware that inherently knows exactly how and exactly when to halt geometrically, the energy cost per operation plummets from 3.70 down to an almost invisible 0.05. It's a completely game-changing leap forward for processing efficiency.
Thinking about the final output of this architecture, we're seeing pure, finite geometry, stepping inwardly, in perfect rhythm. The macro column expands, while the nested turns sequence perfectly inward. It literally replaces mathematical infinities with a bit-perfect physical reality, locking down the computing state flawlessly and symmetrically.
The source material leaves us with this incredibly bold, definitive statement. The curve closes, math is math. Think about that. Instead of relying on abstract subtraction tricks or endless infinite loops to paper over errors, this entire architectural framework strips away the computational hocus-pocus. What you're left with is unyielding, physically grounded code that operates strictly and perfectly within the bounds of natural geometry. Which leaves us with a pretty massive question. If pure geometric balance can execute a deterministic halt to save 74 times the energy in a silicon microchip, what kind of unquantized drift could we eliminate in our own civilizational systems? I mean, if we applied this exact silver diamond balance to macroeconomics or global telecommunications, could we finally halt the top-heavy drift of our own technosphere? It's definitely something to think about. Until next time.